That's my advisor's job, and I am in the support role. So, click. Okay, so I'm Nick Ronnei. I'm a graduate research assistant doing my master's at Michigan State in the geography department, and this is my advisor, Ashton Shortridge. Hi, Ashton. And we are working on a system to bring error modeling to novice geostatisticians like myself. So that's Twitter and GitHub if you want to find me later. Let's get right into it and talk about error, uncertainty, and global digital elevation models. I'm sure that a lot of you in this room are familiar with SRTM and GDEM, the two most widely used global digital elevation data sets. Just a quick little background on SRTM. If you're not familiar, it was collected over 11 days in February of 2000. Version 4.1 was released back in 2008. Covers approximately 80% of the globe between 60 north and 60 south at 1 and 3 arcsecond resolution, and it is widely used. Between 2007 and 2011, there were over 750,000 hits on the website in 221 different countries. So this is a really popular data set, and it's still widely considered the de facto data set for global elevation data. The other data set we're looking at is GDEM, which is from ASTER, which is aboard the EOS satellite. Version 2 was released in October 2011, and it has improved coverage about 99% of the world from 83 north to 83 south, approximately. It has over 691 citations on Google Scholar. So both of these things are really commonly used, very, very popular data sets for research all over. However, it's really important to remember that these are not perfect data sets. In fact, far from it, especially off the bat. So this is some grid errors that are found in GDEM, although they've worked a lot to fix these. You don't see this very much anymore. But you can see that that's just wrong. And errors are caused by several different things. You can have problems with your instruments. You can have problems in pre-processing, processing itself. You can end up with grids like the last slide. You can have voids like this slide. And then you can also have mole runs, which I don't have pictured here, but they're my favorite because they just look so weird. These are commonly referred to as artifacts, and they're relatively easy to find and fix. Like with this, you can just use another elevation data set to fill those voids. The more important thing to remember when you're working with these data sets is that they have a lot of uncertainty. So here, just for a little comparison, we have a LiDAR DTM, digital terrain model, which is what most people think of when you hear digital elevation model. Next to it, you have a DSM, a digital surface model, and then on the far right there, we have SRTM. And you can see that in this digital elevation model, there's definitely trees present. So it's really more of a surface model. And when you're doing calculations like slope, those trees are going to show up, but that's not going to affect the way water flows off your land, for example. So there's a lot of affirmations of this uncertainty. And any DEM you have is going to have uncertainty, but there's a lot of research specifically around showing that uncertainty in SRTM and GDEM. Even GDEM's validation report discusses that this is a major issue. So we have found in our work that there's actually several landscape characteristics that influence how much uncertainty a particular measurement has. These include aspect, slope, land cover, ruggedness, and stack number for GDEM anyway, which stack number is just how many scenes they use to get the value in that raster. So the core of the issue here is that DEMs are used extremely widely, but most people don't consider the uncertainty, and as a result, that uncertainty propagates through all GIS operations that happen after you use your DEM, and so your final results have that uncertainty as well. That's called error propagation. It's been widely studied since the 80s, and basically what that means is you might calculate that your stream is going to go this way, but in reality, it's actually going to go that way. Another application that you might be familiar with is landslide risk assessment. Well, if you have uncertain data, you also have uncertain results, and you might be preparing for disastrous landslides in the wrong places. And that can lead to a lot of doubt and fear, but thanks to the NGA, we can say nope, and the National Geospatial Intelligence Agency is really interested in accounting for this kind of error. And so they have generously provided us with a grant to work on ameliorating it. And so we did a lot of reading. And we found out that conditional stochastic simulation is really the key to ameliorating this error. It lowers your uncertainty by considering the range of possible error in your DEM, and thus you can consider it in all of your future calculations. These are just a few. This is about 9 of the 25 that I read. Just on that topic, there's about 70 papers I've gathered so far for my thesis, and there's about 20 to go. So here we go. This is just a quick overview of how it works if you're not familiar with conditional stochastic simulation like I wasn't. Basically, we have a probability distribution function that determines the range of error. And these errors are non-random, so ignore my perfect bell curve in the background, because that's not actually what the curve looks like. I just wanted a curve. For each value in the DEM, we pull a random value from that PDF and use it and create a new raster, generating what's called an error simulation through a process commonly referred to as regression kriging. And so with that error simulation, we put it together on the DEM, we add those up and create an error realization, which is essentially a possible view of what the terrain might actually look like given the range of error. It's like a maybe. And so if you do that several thousand times over the course of your maybes, you get a better idea of actually. It sounds big and scary, but it really makes sense if you think about it.
So how do you pick your PDF?
So I'm not an expert on that, but I'll address that at the end. The central problem is we have widely documented that conditional stochastic simulation is a great idea. People have even started to build GISs that encapsulate the PDFs with the data and consider these things as you do your operations. But as of now, you still have to be a geostats expert to actually apply this to any of your own research. And so for people like me, that doesn't really work. That just means that I know that my results aren't very good, and they could be better. But we want to change that. So in short, we need systems that are error aware, they need to consider uncertainty, and they need to demonstrate the impact of that uncertainty to users. So we are proposing a distribution system to make that happen. We have developed really good error models. Dr. Shortridge has spent a lot of time doing this, and so now we need to share that information. Basically, we want to look at how this kind of system is going to change the perceived flow of information. I'll talk about this at the end, but if you think about it, this idea kind of changes the whole GIS data model, because you don't need just one data set anymore. You kind of need thousands to get a good answer. And so to make a little bit clearer what I mean on that, we're also going to explore how this would look in 3 very common GIS operations: slope analysis, viewshed analysis, and drainage basin delineation. So I'm going to talk a little bit about where we're at now. This project has been going on since 2008, and it started off as a file system-based thing, and it was pure Python. So we stored raster tiles in a specific directory structure, and then we used Python to access them. We also used Python for data maintenance, access, processing, everything from variogram generation to other exploratory data analysis, and even the error modeling. So we actually have some really cool stuff that Ashton did with his Python code, including a custom datum correction, which, so the coordinate system is the same, but the vertical datum between his reference data for one of his SRTM studies, which was the National Elevation Data Set, NED. SRTM uses the EGM 96 ellipsoid, while NED uses the Geoid 03 vertical datum. And so he actually had to create a custom datum correction. and a wild Fortran appeared, and so he had to actually go through some old USGS Fortran code, create a grid, use SciPy. Well, he implemented his own pure Python KD tree first, and then I re-implemented a KD tree with SciPy's library to do kind of exploratory data analysis and figure out actually what the datum correction was. Yeah.
So you do have the ability in some sense to do ground truth by at least inserting GPS coordinates
That's
at some
correct.
point in your data.
Yes.
As that data appearing, is that getting into your error correction process?
Absolutely, yeah. So that is mostly, that's how we know that the error exists and like what the land cover characteristics are. We do these kind of comparative studies between NED and then also GPS benchmark studies, and those are available for the whole globe. So those feed all of the, like all of that information feeds into the creation of the error models and defining those probability distribution functions. And so additionally, he also had a full Python API for interacting with our Postgres raster database after we moved from the file system over to Postgres to kind of store and maintain all our data. And so that was pretty cool. This is just a little demo of the capability there. As you can see, so on the top we have the National Elevation Data Set, SRTM in the middle, and GDEM on the bottom. And so green is where they're all the same, but you can see that there's a lot of difference between these data sets, actually. I wish the quality of this image was better, but this is all I had. So NED on the top, National Elevation Data Set, which is about 10-meter resolution. SRTM in the middle, and that's at 30-meter 30-meter resolution. And GDEM on the bottom, also at 30-meter resolution. Yeah, that's correct. And it's got a lot of GPS benchmarking that they did to improve it. Yeah. So this is kind of how it worked. We could use Python to pull pieces out and do analysis on them. But that's not really enough for us because we want to share this with the world and not just limit it to people at MSU with our Python API. So the first thing we're going to do is create a system to distribute these error models over the web. And so this is kind of, we're moving away from Python because, as we've kind of talked about so far, people should work in the language that they're most comfortable with. So for example, Ashton has left Python for R because it has a lot better Geostats libraries. So he is more comfortable working there, and so that's where he does all of his stuff now. And so he basically is using Python to pull stuff into R, and it's just getting cumbersome. So we want to make the system work cleaner for people. And so I'm familiar with JavaScript and Python, but I come from a web mapping background mostly, so that's really a JavaScript-driven environment. And so I chose JavaScript to set up our server. We've got a Postgres backend. We're using Leaflet frontend to help people, and I'll show you the Leaflet frontend later, but basically it's a web map that lets you go draw a box around your study area, and you can get all of this error realization data to use in your own work. And so this collection of technologies fits really nicely into our backend where the magic happens. So basically we have these R and Python functions that we've been using wrapped up in Postgres' procedure languages. So we don't really have to change anything there, but it simplifies the access protocols. So we can actually generate these realizations for any study area on the fly. We haven't decided if we're doing that yet or just generating global data sets and letting people pick. That's part of the research that we're doing now to see which is better for speed and everything. And then we all have all the data sitting in here along with our auxiliary data like MODIS and other like land cover characteristics that help us do the modeling itself. So that fits all together with my JavaScript front end, which is just really a standard web map stack using Express and Leaflet as a front end. I guess the interesting stuff for us here at this conference is really the back end. So step 2 is creating, yeah.
Have you considered how you're going to plug into a Jupyter notebook kind of use model?
I guess in what case would you be hoping to?
You've built a bunch of servers, et cetera, and you've listed R and Python, and you didn't list Julia, but the whole Jupyter notebook is about all three of those environments plus
Yeah.
more, right?
Yeah.
Be an excellent web
Right.
engagement and exploratory
Yeah.
participation space.
Yeah, no, okay, I see you. This, like what I'm talking about now is really primarily concerned with distribution of the data. So it's not actually showing, this stage coming up with QGIS is more showing people like how to use these things. And that might be a place for,
So by distribution, you mean people being able to do queries against the database and
right,
get tiles back?
literally
error bars.
pulling out error realizations to use in their own work.
So in other words, it really has nothing to do with R or Python per se, other than it's your Node.js and Postgres system
Yep.
for responding to.
And those hang out in the back end to support all of the database
REST API
operations.
endpoints, that sort of stuff.
Yeah. So my goal and my thesis is to just create a couple of simple models that people can go out and see. And with the QGI, like PyQGIS is going to be my kind of chosen language for going in and doing this. So basically what we're doing is, for example, we have a standard viewshed calculation here. And the way that works, you take your elevation data, you take your point of origin, and you calculate the viewshed. And your possible values are 1 or 0. But the stochastic model says you take a realization, not elevation data, but an error realization, and your point of origin, and you calculate the viewshed, and you still have a possible output of 1 or 0. But then you do that maybe 1,000 times, and your final output ends up a possible value between 0 and 1. So you get a probability rather than a yes or no answer. Essentially, it just allows you to be more confident in your results. So this thing probably makes a little more sense now. And so just real quick, I'll show you kind of where the, oh,
So that's still not the PDF.
no, this is still not the PDF. I don't have pictures of that, I'm sorry. So this is kind of what our website looks like right now to talk about this stuff. Spatial Uncertainty Group at MSU, have all our publications and everything here. But this is kind of where the money happens. So let's see, for example, we have, I'm going to actually, oh, not used to Mac. So when you hear me talking about these error simulations, this is what they look like. They are, they look like random noise, but they are not. They're generated by this distribution function. So essentially, you take this kind of output, and we have, right now, we have a download grid. Sorry, I'm really not used to Mac, guys. And you can just go and download these error simulations for your 1x1 grid or whatever you're looking for. And this is only a 3-pack because it's a demo, but normally the idea is we'd have 500 of these things, or you could choose how many you were looking at. And I'm not going to download stuff to your computer, don't worry. So this is kind of what the interface is going to look like. We'll have more of the drawing functionality over here, different tools for accessing the data. You can input your bounding box and get out your results. Just kind of trying to make it simple and everyone can do it the way that they're comfortable with. So this, like step 3 is distributing the results through that website. But kind of so what is the question for all this, right? I mean, you just watched me stand up here and almost babble for 20 minutes. But the reason that all of this matters is it kind of comes back to Alan McCachran's view on geovisualization. Basically, one point of view can't represent all of your needs. And so for our case, the same goes for data. If you have an exploratory data analysis problem, you're going to use different methods of interacting with your data than if you're trying to publish it. So our whole like Python, JavaScript, everything all together mashed up scenario here just lets whoever is working with the data take that data and interact with it how they want to in the easiest way for them. So the idea for this ultimately is all of this like server highfalutin stuff is just going to go out to GitHub and people can clone this for their own distribution center wherever they want. And you can have an internal Python API, you can have the web map for students in your classes, or you can have, you know, however else anyone needs to access this. The idea is that this thing is going to be completely replicable and we'll share it with everybody. And it just lets people do what they're comfortable with. Additionally, back to that idea of changing the data model, it kind of raises the question, like, will the new shapefile be a zip file, really? Because we take this traditional data model with geometry, attributes, projection, metadata, and we add this probability distribution function of geometric error into the actual data itself. It just kind of becomes part of it. And we think that that's going to kind of transform things. Hoivelink and their group have been working on the data uncertainty engine for a while now, and that's exactly what they're doing on the vector data front. They're taking shapefiles and they just encapsulate these functions, and then every operation is run through a stochastic process. So we're trying to work on something similar as a starting point for raster data, I guess, is where we're at. So thank you for listening to me. I'm happy to take questions. Yes.
Two questions. When people are downloading data, are they just downloading the error distribution, or are you giving them the data as well, like the actual SRTM?
So we haven't planned to do SRTM and those things because they are already available, and most people that are working on that, the data sets already have those.
Matching up.
It's certainly possible, yeah.
And the second question is it only a map-based interface, or can we actually query the API and say, give me something about the box? Because I'm getting fed up with GUI-based interaction.
Yeah, well, so absolutely. So the way we're setting this up, like right now, the Python API, no GUI. That's just Python. And so I haven't really looked into REST. It may be beyond the scope of my work, but that's definitely a direction that we'll want to take this thing as it grows. Because I agree with you, it's a pain in the ass, frankly, to go out and draw a box every time I want something. And while I have the GUI that's going to let you put in a bounding box, if you're studying a bunch of different areas, you want to just be able to do that with a script. So that's on the table, yeah, but not right now. All of it. Yep. We have all of it, all of Modis, all of GDEM, and several different size tile schemes. That was part of the research before I came, was determining which tile schemes are quicker. One node. Yeah.
So your NED data has got a uncertainty of 10 meters, and the other two have 30 meters. So I assume that when you take the three models and you go to a net point, that the uncertainty drops to that minimum data.
Well, so in the research to actually compare it, we upscaled NED to make it an even comparison. That.
So you're throwing away some uncertainty, you're throwing away some accuracy.
Yeah,
Uniform
essentially, yes.
So this gets back to all of my probability distribution function. I mean, at some distance from the net, you're going from a 10 meter to a 30 meter inaccuracy, so to speak.
Yes.
That's where sort of you
Right.
don't want to throw accuracy away.
So I maybe I was a little unclear. We're not actually like on the fly doing the NED comparison. All of the research comparing it to NED was to determine what landscape characteristics increase your odds of error, basically. So that, like, the landscape characteristics themselves are really what's going into the models. And so the residuals are,
Satellite data is what you're saying.
yeah. The difference between NED is, yeah, that's definitely considered.
It's a ground truth error comparison.
Mm-hmm. Yeah. Yeah, so that's high slope regions, very rugged regions. Weirdly enough, certain aspects are more prone to it, and definitely like forest covered areas. Yeah, or even low slopes, even across like plain areas. It's just, yeah. Yep, essentially, yeah.
Is Rowan here? Okay, great. So thank you very much, Nick.
Yeah.
Covered nicely.
Thank you.